And I just noticed that last video had really annoying sound behind me. I suppose I'm sorry that you have to suffer through that. All right, I want to talk about this problem in one other way of thinking about things. We could also think about it this way. Let's scroll down or maybe zoom out just a little bit to give me a little bit more space. I could also imagine if I don't want to rule out that rotation, let's think about this. I'm just going to make some points here. Let's say this point A, B, and C. Let's go ahead and actually think about these as B as my 0 point. And if I go down, I have to go, trying to draw 5 sideways, 5 units down. If I were to break this out each point by point, I'd say, well, how much force does, a unit length have? Well, the force for every unit, the unit force would be 2.5, right? Now, so if I could break this out into a small part, a little dx, say, a little distance dx there, the force on that is 2.5 times the length dx, right? That's how much weight that little section has. Now for these ones, how far does this one have to go? Well, this bottom point here needs to go all the way up to the top. And the next point doesn't have to go quite as far, not quite as far. And then this one at 0 really just stays there. So if I'm using this as my 0 and down there as my 5, what's the distance that each point has to go? Well, for its given x value, it has to go twice as far of that, right? So the x value of 5 has to go 10 total feet. The x value of 0, 0 feet. So this is my force for any given value. And this is the distance that each of those has to go. And so I could sum those up and say, let's do 2.5 dx times 2x. Let's sum up all of those little dx's from x equals 0 to 5. And now I have an integral. So 0 to 5 of 5x dx. When I solve that, it would be x squared over 2 with the 5. I'll plug in the 5. So I have 125 over 2. And these units are foot-pounds, which is the same as 62.5. All right. I thought this was a really interesting problem. I was just trying to come up with something fun. And this popped into the old bean, my old noggin. So we know that a cone is a third of its containing cylinder. All right, so that just means if you had a cone, try to sketch one here, it'd be 1/3 base times height, but the cylinder is just the base times the height, so it's 1/3 of that. We did in class a paraboloid is a half its containing cylinder. So this seems like a conjecture. So we have a curve y equals x to the power of a. X between 0 and 1, a is positive. When rotated about the y-axis, determine a volume that is a ratio of a over a plus 2, blah, blah, blah. All right, find the volume of the cylinder. So this is just saying, hey, if we took this square and rotated it around, we'd have a cylinder, right, with a height of 1 and a circular base that's a radius of 1. So it would be pi r squared times 1. So it would just be pi. So pi units cubed, right? Pi volume units. So that's our containing cylinder for every one of these. So now we're going to think about same idea. If I were to take this square and rotate, I get the cylinder. But now I'm just going to do x to some power of a. Still goes between those 2 points. We have x equals 0 is this the y-axis, y equals 1. So it's this part right here that we're going to rotate around. You could also think if this was just, if A was equal to 1, this would just be a straight line, and we'd be getting a cone. So for this problem, we're just going to do the shell method. So I can use a nice dx still. I could use, the washer method, but it becomes a little bit more gnarly. So it's going to be 2 pi, the radius x, and then the height of this is actually always going to be 1 minus x to the a dx, and x goes from 0 to 1. So now we just need to solve that. The 2 pi hangs out. Just for our sake, I'm going to go ahead and distribute that. Very good. Let's integrate it. So the 2 pi hangs out. We have in there x squared over 2 minus would be x to the a plus 2 over a plus 2. Going to plug in a 0 and a 1. When I plug in the 1, I get 2 pi times 1/2 minus 1 over a plus 2 minus 0. I make it a single fraction. And you can verify this. I'd have 2 pi, I'd have a plus 2 minus 2, so a on top, 2a plus 2. Just gives me pi times a over a plus 2. So notice this is a over a plus 2 times pi, but pi was the cylinder, so this is the ratio of the volume in relation to the volume of the cylinder. So the pi is the volume of the cylinder. I multiply by a over a plus 2 to get the volume of this thing. So that's what we're doing in part C. So in part B, we do pi a over a plus 2. Compare it to the volume of the cylinder divided by pi. I just get a over a plus 2. Hot dog. If a equals 1, this is 1/3. Yes, because it's a cone. If a equals 2, that'd be 2 over 4, so 1/2. Oh, I should have said this is, the cone. If this, we get 1/2 when a is equal to 2. That's a paraboloid. So those are both in the problem. Yes. If a equals 0, that's kind of a funny one where I end up with just this little line segment that's rotating. And so a line segment that's rotated like that is going to have a volume of 0. So I get a volume of 0, and that makes sense. For a being negative, it's funny because this ratio will give me negative values. So think about like -5, right? You'd have -5 over, I guess -3. I guess it would. Some of them give me negative values depending on what values of a I pick. But what's weird about this and why it's a little bit funky is that shape is not actually contained in that box anymore, right? It's outside of it. And so it kind of falls apart. All right, these last two, these are fun ones. Here we go. So we want to show this pyramid is 1/3 the area of the base times the height. So the volume of this would be the cross section where x goes from 0 to its height, to h. The cross section, though, using our hint, is some constant. We'll call it c times x squared, because if I go out x far, this height there is some constant c times x, and we're squaring that. Dx. So you integrate that, you plug things in, so you get c squared h cubed over 3. But the 3, this could be written as 1/3. C squared h squared is this area, the area of the base. And there's one more h left over, times the height. So that's how you can get that formula. Now this is a really cool one. We talked about this one in class, Gabriel's horn. All we really need to do, I could do it a little bit formally. We talked about sort of infinity there and 1. I could talk about it. Let's talk first going from 1 to some value b. And then think about what happens as b goes to infinity, where we just have, using our disk method, the height is 1 over x, so we square that times pi, and you integrate this. So when you integrate that, you square it, so that would be 1 to the b. We're going to take the limit still. Pi of x to the negative 2 dx. We're going to take a limit in a minute that's coming along for the ride. That would be pi times negative 1 over x. Think about plugging in b and 1. So I'd have a pi hanging out. We're going to be thinking about the limit as b goes to infinity of that value. So we have here negative 1 over b minus, so plus 1. But as b goes to infinity, that's 1 over infinity, this thing goes to 0. So we end up with pi times 1. So we just end up with pi. So the volume of this infinite shape has infinite length. It's just a finite value. All right. Hopefully this is helpful.